Bom, muito bom dia aos amigos e amigas aqui presentes da FAPESP. Nós vamos iniciar a 5ª Conferência FAPESP do ano de 2023, o mundo dos meios porosos e da agricultura e do meio ambiente. Conferência que será proferida pelo professor Rien van Genuchten, do Departamento de Energia Nuclear da Universidade Federal do Rio de Janeiro e Departamento de Ciências da Terra da Universidade de Utrecht, na Holanda. E eu convido então para compor a mesa de abertura presidente da FAPESP, o professor Marco Antônio Zago. Representando a Comissão de Organização das Conferências FAPESP, professor Oswaldo Bafa Filho, da Universidade de São Paulo. O nosso moderador do evento de hoje, Dr. Silvio Crestana, da Embrapa Instrumentação Agropecuária. E o nosso conferencista, a quem agradecemos a presença, professor Rien van Genuchten. Vamos sentar? Professor Zago, por gentileza, a palavra está com o senhor.
Muito bom dia, minhas amigas, meus amigos. Eu vou falar em português, embora depois tudo será conduzido em inglês e haverá tradução. Eu quero cumprimentar a todos, dizer que é um prazer estarmos fazendo mais uma das nossas conferências. Disse ao nosso conferencista que não se preocupe, porque a audiência fora é muito maior dos que vêm aqui. Os que vêm aqui se beneficiam de ter o contato pessoal e podermos conversar, mas a grande parte das que assistem pelo YouTube. Então, bom dia, quero saudar os nossos companheiros de mesa, a começar do nosso conferencista, não é? Rien van Genuchten, que nascido na Holanda, depois se transferiu aos Estados Unidos, onde trabalhou, e finalmente trabalha agora aqui no Brasil. Então, trabalhou em 3 continentes e em áreas muito diversas também. O que é sempre muito interessante, não é, professor? A gente não fazer nada rotineiro, né? Sempre buscando coisas diversas na vida. Mas eu suspeito que a sua proximidade, embora seja físico, matemático, a sua proximidade com a agronomia começa lá na própria Holanda, não é? Desde a família e depois na universidade que eu nunca vou conseguir falar este nome.
Wageningen.
Mas não é assim que os holandeses falam. Que é onde está provavelmente é o melhor centro de agricultura do mundo, de alta qualidade. E é compreensível, então, que tenha sofrido esse tipo de influência. Quero saudar o nosso professor Oswaldo Bafa, que é membro da comissão organizadora, junto com o Fernando, com o Jolie, com o Esther, que estão aqui, tá certo? E agradecer a presença do Silvio Crestana, outro físico que migrou para a agronomia. Foi presidente da maior empresa, da mais importante iniciativa do Brasil na área de agricultura, que foi a Embrapa. Então, foi um prazer muito grande tê-lo aqui e agradecer. Então, era isso que eu queria fazer, cumprimentar a todos, saudá-los e dar oportunidade para que falem. Mas, antes de começar, eu quero dizer que nós estamos, mais uma vez, muito entusiasmados com o desempenho da nossa comunicação da FAPESP. A agência FAPESP, que todos conhecem, pela 3ª vez é finalista de um prêmio, de uma disputa que existe anualmente a respeito das agências mais expressivas em termos de comunicação de ciência. Nós ganhamos 2 vezes já e novamente somos finalistas. A agência FAPESP é finalista, junto com o G1, com uma série de outras agências aí. E, paralelamente a isso, a nossa jornalista, membro da agência FAPESP, a Karina, também é finalista nessa disputa, mostrando que a FAPESP faz um trabalho muito importante aí de divulgação de ciência e que a nossa agência, da qual nós temos muito orgulho e queremos cumprimentar, então, aqui, publicamente, a agência FAPESP e a Karina pelo seu desempenho. Muito obrigado.
Muito obrigado, professor Zago. Ouviremos a seguir, então, o professor Oswaldo Bafa, membro da comissão organizadora das conferências FAPESP.
Bom dia a todos. Eu também gostaria de saudá-los e agradecer a presença de todos que estão aqui na nossa Casa da Ciência e da Inovação do Estado de São Paulo, que é a FAPESP. Como o professor Zago falou, esse é um local privilegiado, onde a gente tem se encontrado para rever amigos, fazer novas amizades e pensar em novos projetos de pesquisa. E como já foi falado, nós temos uma comissão que cuida com bastante carinho de organizar uma lista de eventos com personalidades. E hoje nós temos aqui o professor Rien, que vai falar sobre um tema bastante interessante, né? Eu confesso que tinha uma total ignorância sobre esse assunto, até que nós começamos a pesquisar, e vocês vão ver a importância do que ele vai falar aqui para a gente. Fazendo uma analogia bastante simples, né? Se a gente pensar que a atmosfera tem cerca de 10 quilômetros e a gente depende fortemente dela, né? Quando a gente olha para baixo e vê o solo, nós estamos falando de uma coisa bastante delicada, cerca de 1 metro. Se a gente não tratar bem desse metro, as coisas também podem ir para o brejo, tá certo? A gente pode se dar muito mal. Então, esse é o tema da nossa conferência, né? Extremamente importante. O professor Rien, como o professor Zago falou, é uma pessoa de vários continentes, né? Holanda, Estados Unidos e, finalmente, Brasil. Ele foi um pioneiro nessa área de pesquisa dos meios não saturados. Tem um conjunto de equações que é bastante utilizado, que leva o nome dele. Ele tem uma produção científica de 40 anos, bastante expressiva. Foi ganhador de um número enorme de prêmios, sendo que o último foi esse ano da Fundação Wolf de Israel. A Fundação Wolf é uma fundação que todo mundo que ela premia geralmente ganha um prêmio Nobel. Se tivéssemos um prêmio Nobel em ciência do solo, acho que o professor Genuchten seria o próximo a ser contemplado. E, bom, além dessa atividade de pesquisa intensa, ele é uma pessoa que não ficou fechada nos laboratórios. Ele procurou interagir com a comunidade, procurou formar pessoas e procurou fazer um trabalho, vamos dizer assim, extensionista, como a gente chama, que é cada vez mais cobrado de nós cientistas. Ou seja, a gente tem que sair do nosso laboratório, da nossa torre de marfim e chegar à sociedade. Então, acho que ele é um paradigma nesse aspecto. Então, eu fico muito contente de tê-lo aqui, tá certo? De estar fazendo essa conferência. Eu não vou me alongar, porque se eu for ler tudo que eu coletei aqui, acho que ia demorar mais do que a conferência dele, tá? Bom, então esse é o primeiro recado que eu queria dar. Eu queria aproveitar também, acho que é agora, né, de chamar a atenção para as nossas conferências, para as nossas escolas FAPESP, que vai projetar ali. Nós estamos organizando 2 escolas interdisciplinares. Uma é na área de ciências exatas, naturais, engenharia e medicina. A outra na área de humanidades, ciências sociais e artes. É uma escola que tem um formato totalmente diferente do que vocês já viram. Ela está inspirada em outros exemplos, como os encontros da Fundação Lindau, desculpe. E a Escola de Ciências Exatas se encerraria hoje o prazo, mas a gente recebeu uma série de solicitações pedindo para prorrogar um pouquinho mais. Então, as pessoas vão ter 1 semana a mais para poder enviar suas inscrições. Então, eu pediria a todos que nos ajudassem a divulgar e estimular os seus pós-doutorandos que estão com bolsa vigente a participar desse evento, que vai ser certamente uma experiência marcante e diferenciada na vida deles. Bom, com isso, então, eu gostaria de encerrar minha fala e, mais uma vez, agradecer ao professor Rien pela presença aqui hoje. Muito obrigado.
Então, gostaria de convidar o professor Rien para a sua apresentação e solicito ao professor Silvio, professor Zago e professor Bafa que se acomodem na plateia para poder assistir a apresentação. Muito obrigado. Por favor.
Ok, muito obrigado a todos, Professor Bafa, Professor Fernando e outros. Primeiramente, desculpa de falar inglês. I always, sempre, I rely on Betty May, my wife. She's so good. She's actually a Paulistana. So, but desculpa de falar inglês. Português e eu não concordo muito. I am very excited to be here. You know, I heard so much and have been interacting a little bit with people from FAPESP in Sao Paulo State in general. Think about Sao Paulo here, Rio Claro, Pernambuco. No, what is it? Yeah. So it's great to be here. I would like to thank everybody again that made it possible to come here. Again, very much my wife and so on. What I want to do is paint a little bit the things of my career, you know, and I will start very much in the beginning. But the idea really of the bottom line is that everybody has their own path. And mine was, I don't know why, but it went from one place to another place, and here I am, you know. A lot of what I did went 1 year in, 1 year out. I don't remember too much anymore, but in a way it's kind of nice to look back a moment, and I hope you will enjoy. Let me see. This one. Okay, yeah, good. So my focus has always been, I would call the near surface environment. And so very much the unsaturated zone, some people call it the vadose zone from the Greek shallow. Critical zone is a little bit broader. And then the interactions, of course, with the atmosphere and groundwater. We live on the, let me see if I can put this, yeah, here. We live at the top of the vadose zone, and the vadose zone in a way protects us from messing up the groundwater system, but also protects us in terms of the interactions with the atmosphere. Unfortunately, we're changing the surface of the Earth in many, many ways, probably too much. And you know, when I'll show you some slides at the end, that we have to be very careful what we're doing in the long term. My work with the vadose zone, or the unsaturated zone, really started many years ago. Let me see if that goes. No, I have to do this. Ah, yeah, this, okay. So what I will do is actually, I will go over a little bit my career. It started quite a few years ago, as you can see, in the 45. So I've been around quite a few years. I was in Holland for a while. I went to Las Cruces, New Mexico. I'll talk to you about a few years at Princeton. Basically, my career was in Riverside, California. And then in 2008, I thought it was about time to do something else, and I met Betje, and so we went to Rio, and I still have a appointment also in Utrecht, as well as some association still with Rio Claro. So where it started all, let me see here. was a little town here it's called Vught, a very small little location in the southernmost province, North Brabant, because we are, Brabant also is in Belgium, where it started in 45. And I grew up on a little farm, and I want to show you here a couple of pictures, many, many, many years ago. And so my dad was actually, had a fazenda, a farm. We had to help a lot. We had to work very, very hard, very conservative person, but also very progressive in many ways. And he was really key in me going to high school, which was not common. I want to mention one more thing here is that the place we grew up was very close to a concentration camp. That's the only one we had in Holland, called Vught. And so a lot of political prisoners, also Jewish people, and regular people that were condemned for other things. And there was also what they call an execution site here, Fusillade-plaats, which was only about 400 or 500 meters from our farmhouse. So you can see when prisoners escaped from the camp, where do they go? So my dad had a lot of connection at the time with the underground. So here you see a family. We were with 11 children, so quite a lot. Let me see here. So this is me here, my older brother, my older sister Betsy, and quite a few. There were 2 or 3 more that are still not on the picture. This is the formal picture. You look actually more the day-to-day things. We were a little bit less well organized and so on. I'm here, the second one from the left, and anyway, probably about 10 years old or so. But anyway, my dad, we worked very hard on the fazenda, but he was very, actually, let me go back a moment. He was very progressive in terms of us studying, which at that time was not quite popular. Actually, my sister was not even allowed to go to the high school. I went to a high school in Boxtel, which was about 10 kilometers. I had to go one way, rain or shine, with the bicycle. So it was quite a lot of work, but with a lot of fun in many ways. Because he was, in that sense, very progressive. He wanted all his kids to go to high school. Now it's different. Now everybody goes to high school or further. So I went to high school, struggled a little bit, especially with more the social and other scientists, but I was pretty good in mathematics. Actually, at the end of high school, I went to had a psychological test, and this is really interesting. So the person said, to draw a painting. I draw a painting of a big tree because we had a painting at home of a tree. So he concluded that I was not really suited to go to a good university. So he sent me to an agricultural university, which at that time was not even called. It was called the agricultural high school, Wageningen. Later became a university. But I could go there. Nevertheless, I would have some trouble. But then when I arrived, I immediately had contact with a Professor Rootselaar here. You can see here at the top. And he was actually impressed how I answered some of the questions in his math course. And in fact, later he even tried to get me to switch to do mathematics at the University of Amsterdam, because he had an appointment there also. So that was great, because I had a small little bolsa, how you call that, from the government, but I got also a little bit paid by the math department. There were 2 other professors there that helped me through the system. I was a little slow in many ways, but finally finished it. And one of the things I did was actually with Professor Nuchtere, I was doing a part of my master's I spent a year in Madagascar, in you know, the south of Africa there on the big island, and to look at irrigation, drainage a little bit from a practical point of view. Unfortunately, I got all kinds of diseases like malaria, what was it, hepatitis and so on. And so when I did my master's, let me see here, I made two reports. One was on drip irrigation, but the other one was on that study we did in Madagascar. But he said, you know, it's better not to go back to tropical areas. So that was really my focus. So I didn't know what to do. So I talked with some of my, let me see if that goes, you know, when in 71 I got my master's, he said, what need I do? Why don't you go to the States for a year? So a year, okay. So I wrote 5 people in the States, 2 answered, and only one said, you know, I can probably cover for you for a year. So, and that was actually a guy called Peter Warenga, and he was in New Mexico. Here is Las Cruces, New Mexico, very close to the border with Mexico. I had to look at the map where the heck that was. So I went there, and you know, I had to work on some field trials. Actually, he was interested in me because of that trickle drip irrigation project I did at that time in Wageningen. So I went there, Pete, and then Pete said when I arrived, unfortunately, there are 2 or 3 things you need to get used to. First of all, you have to change your name, because Van Genuchten, Van Genuchten, they don't know how to pronounce that. Secondly, I can only pay you if you enter the PhD program. And that was really not my intention at all. You know, I just wanted to go for a year or so, but you know, I needed the money, so I entered the PhD program, and that really entered my life. So Peter was very key in terms of getting into the rhythm of being a researcher. Then he wanted me to work in the field. Yeah, so he tried to make me practice a little bit how to you know, manage the soil. So this is actually a picture of along the Rio Grande there in New Mexico. But he quickly noticed that I was not really suited for a lot of field work. So then he, let me see here. Then he decided, you know, it's better to for him to work on some more theoretical stuff. The math, he was quite interested actually in some of the things. So he put me on some laboratory experiments, and then especially how to analyze the data. How to do the experiments wasn't a problem, because Peter Warenga was very good in that. But what transport models to use, how to get these solutions at that time. This was in 71 I went there, 72, 73. It wasn't quite clear at that time still. And then how to fit the data, how solutions to the data, how to analyze the data. So that was really, I enjoyed very much, whether it was the mathematics, analytical, or numerical studies. And so the focus there was actually, and this is a later setup that Pete used and I worked with at that time, where we did these displacement transport experiments that would be added to a column, and you would then, with a fraction collector on the vacuum, collect the effluent curve, we call it. And then we plot that versus time, or dimensionless time here, pore volume, which is the amount of fluid going through the column divided by the fluid in the column. So if there is no adsorption, you will get a retardation factor here, R, of about 1. And anyway, the dedicated transport equation was the advection dispersion equation, the ADE equation. But there were at that time very few good solutions. And so I started spending on analytical solutions of that thing, and then applying a parameter estimation procedure, how to best optimize the effluent curves. Pete wanted me to look at not just regular soils or very homogeneous soils, but also on soils that were aggregated, that showed problems of preferential flow, structured soils. And so he made me to look at, actually in this case, an aggregated soil. This is a breakthrough curve of a pesticide, 2,4,5-3-chlorophenoxyacetic acid, if I remember. You can see here the fit is reasonable, but not very good. And if you have lots of preferential flow or non-equilibrium flow, it would come out even earlier, and then you get more tailing. The surface above the curve is always the same, you know, the retardation factor, especially if you have linear sorption. But the shape will be different. So I spent a lot of time at the time on these, I call it dual porosity models, mobile-immobile models, or two-region models, where you assume that most of the water would go through the larger pores between the aggregates and then imbibe somehow the solution into the smaller pores. And then here we assume that the flux in the through the smaller pores, the aggregates would be zero. And this will be a simple first order approximation. Later we looked at more exact solutions. I'll show you that later, where we actually use the fusion equation. But anyway, I worked with these type of solutions, and of course, I got some better descriptions here. Not that it necessarily proves that this is completely the correct way to doing it, but at least it fits the data well. Many examples can be shown. That was basically New Mexico. I didn't know what to do. Should I go back to Holland or not? And then at the last minute, oops, what is this? Okay. Let me click through it. Okay, so then I didn't know what to do, but apparently there was an opening at Princeton, somebody looking at for a postdoc, so I decided not to go back to Holland, but stay a few years in Princeton, where I became basically a postdoc. They call it a scientific collaborator, but basically a postdoc position with George Pinder. That was in 72. No, in 74, 75 I went there. He was there at Princeton from 72 to 89, something like that. And so there I actually started looking at numerical solutions, even though analytic solutions were my favorite. We started looking at these numerical solutions. And let me see if I can put that cursor down. Okay, well, for the cursor, we need okay. So we started looking at numerical solutions of what I call the Richards equation. So that's for a variably saturated flow. This is just for one dimension. You can put it in 2 and 3 dimensions. And the advection dispersion or convection dispersion equation, but then for transient flow conditions. And so I started working on those solutions, and he was very much interested in using not just regular numerical finite element approaches with linear basis functions. He was very much interested in cubic, or what we call Hermitian finite elements, where you not solve just for the pressure head here in this case, or the capillary pressure, but also for the slope, the h dt, or the s dt, the h dx, the slope versus distance. So instead of one parameter at each point, you would have solutions for the pressure head and the spatial slope. So that would make the solutions continuously differentiable. Later, and then I spent quite a lot of time on that. There's actually a paper that came out in Water Resources Research, where we tried to fit that to some data that were collected by Art Warwick in Tucson, Arizona. and it worked relatively well. He convinced me that Hermitian finite elements were the best solution. Unfortunately, that was not really the case. The lower elements are much better. And actually, when you go into one dimension, I don't know if you're familiar with this, and you do what we call time lumping of the mass lumping of the time derivative, it becomes exactly the same as regular finite differences. And then also, we didn't use the here. We didn't, in the end, not using the pressure head-based equation, but we started working with the mixed equation. This is actually some work that Mike Celia did and later, where first you do the mixed equation and then you transform that in some way or another to get a much more stable solution. But that was done much later, that we incorporated in our general models that came out. But anyway, I worked on this. One of the things of the Hermitian solution was that it was not very consistent with the hydraulic properties that we used. And very popular at the time were equations. Let me see here, that I really wanted to have an equation that I could use in the numerical solution that was consistent with the numerics. And the Brooks and Corey equation was popular at the time. It's really an exponential function. HA became known as the air entry value, but it's really a power function, where between some residual value, and of course, when you go way up, you have to cut it off at the saturated water content theta S, and that HA became known as the air entry value. And didn't work very well, both in terms of the numerics, but also in terms of many data sets that I looked at. And so then I tried to change that a bit. In fact, I suggested we should use a slightly different equation that gives, here you can see a soil water capacity, that's the derivative of the water content versus the pressure head, that will be continuous. So the slope would, the retention curve would not have this sharp break here at the air entry value. And this worked very much numerically, and then also it was better for most or many soils, porous media that I looked at the time. I didn't spend very much time on this at that time. Here you can see the difference if you fit that. So I wrote a little program to fit that to data. This is for a sand system. So you can see here the Brooks-Corey and our equation here gave a much better fit. You also see here variable n and n, or you can actually restrict these values, which is sometimes good when you have poor data, because what the variable m and n does is that the curvature here at the high side is independent of the curvature at the low side. But generally we have poor data, and so we try to fix this in a certain way that it gives also a prediction of the hydraulic conductivity. I will mention that in a minute. But if you look at these equations, they're really very much the same, except that, you know, HA over is roughly 1 over alpha, and the only thing I did was add this 1 in the denominator, and it made it smooth. And then this was then combined with what we call statistical pore size distribution models. There were a lot of those things available, especially in the oil and gas literature, the petroleum engineering literature, Purcell, Burdine. Another fellow called Moalem actually also formulated something that I thought was a little bit more accurate. The idea there is that you approximate the porous media as a system of cylindrical tubes. And then at each point, you assume that all the pores at a certain H value, pressure head, all the pores that will be larger would be filled with water, and all the pores would be smaller than water. And then there are, again, many different models available, and some of them have different assumptions also about some people say, let's twist this connection, and then there is a certain probability that a small pore would connect to a large pore, and so on. So there are different ways of doing things. The one that I worked with was Mualem, Haji Mualem, and I met him a few times later. But anyway, he was not overly interested in it, but we put it out anyway. So again, we use a certain law, the Laplace-Young's law, for the water content. That gives what the rise is as a function of the radius. And then we integrate all these pores to get the water content. And then we use Poiseuille's law for the flux, to get an estimate of the flux. And we could do that then for different pressure heads or water contents and get these curves. And so here's then an example. This is of a porous media. I think we did that with Los Alamos National Lab, but you had caisson data and laboratory data. But the idea was to fit the retention data, the capillary pressure saturation data, and then predict as best as we could the hydraulic conductivity, which is unsaturated, which is very difficult to determine, especially if it is in dry systems. When it dries out, at the very low water condense of pressure heads. And then I developed a little optimization program. In this case, they actually measured also the unsaturated conductivity data. But generally, it's just a prediction where we use the saturated hydraulic conductivity to fix the curve in the wet side. Anyway, I did that, and I really did not spend too much focus on it. I put a little program, a report out at Princeton. You can see here Rien van Genuchten, water resources. That was in 78. It came out, and I had a card deck. I sent it to quite a few people. But then I thought that was it. But then later, more and more people started using this, and they pressured me, especially Jacob Dane and very others. Hey, Rien, you should really write a paper about it. So I wrote a paper that came out actually a few years later, in 1980. I was already in Riverside, California. I submitted that to Soil Science Society of America. It came back, major revision, and even the title was not overly creative and so on. But I persisted, I revised it, and I probably would not be here if that had not come out, because it's being used, it is referenced about, 30,000 times or so, and not just in soils, but in all kinds of porous media. Think about fuel cells, diapers, it went all over the place. So that probably is the main thing where people know me about. Anyway, next. Later, when I was already in Riverside, then we organized actually a number of workshops where we invited quite a few people from around the world. We got funding from different organizations. We did that in 89. You can see here, where is it, in 89, and then also one in 97. This is actually a picture of one of the people, one of the workshops where people attended. I'm not going to go over who, the most known ones, but here you can see here, where is it, Art Corey? Where is my there is Art Corey here. You can see quite a few others. Pachepsky here, and so on. I'll leave it by that. Anyway, so that was Princeton, basically, with a little connection. Then I went to Riverside at the US Salinity Laboratory. So again, I decided, well, let me stay in the States. So I went there. First I was, because I didn't have an American passport, I was hired through the University of California, Riverside. I stayed there for quite a few years until they needed a new, what we call a research leader. And for that purpose, actually, I had to give up. I had to become an American citizen. And at that time, the Dutch system did not allow dual citizenship. So I lost my citizenship, Dutch citizenship. And then later, that was in 2008 or so, they changed the laws and I could regain my Dutch citizenship. Anyway, I was not overly happy to become an American, but in a way it was just fine. Anyway, there we worked on quite a few topics. The most important one probably was the Hydra software for water flow and contaminant transport, where we improved the numerical solutions. We went to linear finite elements, as I mentioned, and not Hermitian anymore. STANMOD, which stands for a suite or a studio of analytical models. So I really enjoyed still working on those things. I will show you one or two examples. Then the hydraulic properties, how to analyze that. So we had that SoHy program of Princeton, so we improved that a little bit, Red Sea, as well as, and this is Marcel Schaap, how to predict these curves, which are crucial if you have less information, for example, only soil texture or bulk density or so on. And then I also spent some time on water and salinity stress, how to get better estimates of water uptake by plant roots. So one of the things was, the analytic solution I developed, we worked on during my PhD, but we extended that and very much looked at the value here of the mass transfer coefficient alpha. And so for that, actually, I did a lot of work. I worked very much with two guys here, Feike Lai, who's also a Dutch guy, and Nobo Torida. Actually, Nobo Torida was interesting because he did his PhD in Japan, and he wanted to come join the Salinity Lab, our group in Riverside, for half a year. He ended up staying 3 years, so he really enjoyed it. But anyway, this is just extending the analytical solutions to 2 and 3 dimensions. Let me see here. And then also, and this is an analytic solution there that Feike and Nobo with me a little bit. You can see it's quite complicated. It has integrals here. Where is it? An integral. And then all kinds of RFC and whatever functions. So it was not necessarily easy, but it was very appropriate. So you can see that solution again. And then with Jurka Simonek and Mirek Sejna, we developed a user-friendly program around it called STANMOD, or Suite of Analytical Solutions. So we use that both the equilibrium models, the non-equilibrium models. We looked also a little bit at stream tube models and a number of other things. Another problem we looked at is very much that alpha. Remember in the dual porosity model? And for that, I looked a lot. This is another example. I just, for the heck, showed you to impress you a little bit. But and it's so funny because if I look back now at my notes, how I did it, I cannot do it anymore. Yeah. But I spent a lot of time. These are Burr and Bai functions. So actually here, when you look, these are Kelvin functions or something. And it was quite interesting. But the idea was here to look at water flow and contaminant transport through a marker pore, and then you would have slow diffusion of the contaminant into the surrounding soil. So that would be a cylindrical kind of transport equation, and then they would be connected. And you can see here that the immobile concentration would be the average concentration in the cylindrical soil mantle around the marker pore. It would be the average. So this would be a connection with the more approximate dual porosity formulation I showed you earlier. And I actually forget about the left side. but it turns out that these first order approximation, I call it, work very well for the cylindrical micropores, but not necessarily for soils that are made up of spherical aggregates that have a very large surface area compared to the volume. And micropores have a small surface area of the contact between the micropores and the soil. And then it works very well. And it's kind of funny because many papers in the literature at that time suggested that the first order approach doesn't really work because they were comparing that with cylindrical pores, with spherical aggregates, sorry. But the cylindrical pores, actually, it works quite well. And I think in most cases, when you look at preferential flow, well, here's a summary of that. So the alpha is a function of the geometry there, as you go. But also, actually, this is important, I wanted to mention, it's also a function of the scale of the transport problem. And likely, alpha decreases as a function of the scale. A little bit like the dispersivity for those that are familiar with you, the dispersivity, which is the ratio of the dispersion coefficient and the pore water velocity. We know that increases as the scale increases, maybe to a certain maximum. For alpha, that actually decreases as a function of the scale. And it really implies that if you do laboratory experiments about a certain contaminant, you have to be careful if you apply that to the field scale, because that alpha may not necessarily work. So, but it's really an issue that keeps us very much busy, is, you know, the transport in structured or microporous media. I worked a lot with the aggregated soils, or you can here see structured soils, fractured rock, very much the same. In California, many other places, we have a very high clay soils. So we get drying cracks, and then they would swell again, and so on. In fact, sometimes these cracks are important because it's the only way you get water into the soil. Depends a little bit on the type of clay that you have. And then just micropores, you know, think about wormholes and root channels. And then, you know, there are quite a few examples here. This is actually one that was done at Utrecht University, where just an experiment with some dye that goes down. And you can see that it's really not a very uniform displacement down, but it goes more into what I think the cylindrical micropore type procedure. Anyway, so we looked a lot at this also for water flow. The problems there is not just the processes involved, but then also we still struggle a lot with the type of models we use to put the processes into some formal formulation. And then, of course, the parameters involved with these models. And then the question is really, how do we translate what we know about the processes into the various models? And there are many, many different approximations. I should say, you know, with the hydrous codes that we developed, I'll mention it in a minute, we have both dual porosity models that assume that water goes only through the micropores, or we have dual permeability models where we assume that both the micropores and the micropores allow water flow, but with, of course, the water flow in the micropores being much slower, and then some interaction between the two regions of the system. So that was STANMOD, and now here the hydrous. So this is the numerical solutions we again use at the Richards equation. Actually, L.A. Richards was a scientist that also worked at the Salinity Lab, you know, and in fact at that time I still met him. Yeah. He was already retired, but he visited. So he was a big, one of the big guys that we looked up to. The advection dispersion equation, and then also we included a heat movement. And then the packages, these are some of the, or most of the processes that are included. So we have water flow here at the bottom, at the top, root water uptake, very much a focus, contaminant transport. So we slowly, especially with Jurka Simonek and Faika Lai a little bit, and Marek Zena in Prague. But anyway, we extended these things to colloid various transport, colloid facilitated transport, decay change. We also have some versions that was done with Diederik Jacques in Belgium, where we coupled the hydrous codes with multi-component transport, and this is, in this case would be the FreakC program. We have a very tight coupling between the two, constructed wetlands also, heat transport, and a number of other things. And then very important, we spend a lot of time, especially Jurka and Marek Zena, to put this in very friendly GUIs. So people would actually use it. And that actually brings me then to the work we did in more of a practical side in Riverside at the Salinity Lab. The focus, of course, was irrigation and drainage. I was very fortunate because they had lots of data, and I could work with them to get a little bit of a conceptual basis on them. Most popular at that time were fertigation. You can see here, you know, on the left side, not very efficient. And then here the salinity problems. So we focused on that. And actually, you know, the question would be if these kind of conventional irrigation methods are still are sustainable. We see more and more work going towards drip irrigation, especially subsurface drip, to minimize the contact with the air, but also to minimize unneeded flow through out of the root zone. And then we worked with, this is actually an experiment that was done in the Central Valley, where they spent weeks and weeks doing these experiments. We have a subsurface drip line, and then interesting is for them was, you know, how this wetted, you can see here how the wetted area of a soil would change if you have a different soil textures. So if you have a sandy soil, it would be going much more down than with more fine textured clay soils. This was kind of an average soil. This was done experimentally and numerically. You can see actually we could do that in a question of 15, 20 minutes rather than 2 weeks. But anyway, it would give some guidance, not necessarily that everything has to be done experimentally. And another example, sometimes some of you may have seen this, where actually Altaf Sial, a guy from Sindh province in Pakistan, he came over. So we looked at pitcher irrigation. So these pictures are being used by people, you know, just to bring drinking water, sometimes also as an air conditioner, because it evaporates from, you know, through the walls of the pitchers. And then if you had a good baker, he could kind of manipulate the conductivity, the permeability of the walls. Anyway, we did also some numerical exercises for pitcher irrigation here. You can see here the difference between regular kind of medium and fine textured. Oh no, it was here. The concern was if we use a smaller, a large pitcher, because the large pitcher was much more expensive. And so, but it didn't make too much difference in terms of the, it's more the soil texture what determines the distributions around the pitcher. Of course, you know, you cannot use this for large-scale mechanized agriculture, but in the back of your home, you can plant these pitchers and be actually quite sufficient, sustainable, or careful with the amount of water that you use. Okay, let me go further. Then we also spent some time, I'm going to skip this mostly, on root water uptake. The kind of the classical approach would be one that Fettes did, the guy from Holland also. It's very popular. It says that the uptake of water from plants would decrease when the soil gets drier, or where the pressure head decreases or increases, depending on the minus plus sign. And he actually used this particular formulation with two. If you have a very high evaporation rate or potential transpiration rate, it would go down much earlier. And then if you have a slow kind of system, it would go, it could maintain the potential rate much higher. So this is the actual uptake rate multiplied by a stress factor here. It would diminish the potential uptake rate, which you can calculate from the potential evapotranspiration rate, and then the root distribution, which integrates to 1. That's what's done. But we looked at some alternative equations that actually get rid of these sharp breaks, a little bit like the Brooks score. In our equation, we didn't like that. And so I worked that out quite a lot along the lines of the hydraulic properties at the time. Actually, here's some example of some data. Again, you can see here much more smoother, rather than what we call here a threshold slope model that was kind of popular and still is popular. Anyway, we spent a lot of time on applications of hydrous. Certainly, you know, the focus was on agricultural chemicals, but the basic equations are the same for everything else in the industrial, environmental, whatever, you know. Think about, you know, radioactive waste here, capillary barriers, this and that. So a lot of the different organics, virus, bacteria, transport. So we, and now phos and the rare earth elements are becoming quite popular. So there are some subroutines that we included in hydrous, and Jurka Simonek and Mirek Senjan were the most active in that sense. We spent a lot of time on these codes. We did a lot of publications, a lot of tutorials, short courses. Actually, I really enjoy showing this picture. And I call it the hydrous missionaries, but we traveled all over the world, basically, all continents. This is Jurka Simonek and myself. In this case was a short course in Prague. So we did quite a few of these short courses. Anyway, so that was until about 2008, and I thought it was about time to leave the Salinity Lab. So I joined my wife here in Rio. Did do a lot, much of the same, and some not of the same. And actually, the things we did was actually looking also at the larger scale a little bit, as well as really the small scale, the pore scale. And the pore scale is really where the processes occur. So this is a focus that I think is very important to understand the basic mechanism. This was done with the pore network model. Also, you look at other approaches. So these are some of the applications that we looked at. Norm mining sites here in Brazil. So this is natural occurring radioactive materials, landfills, a radioactive waste repository. This is actually quite interesting. Betje May, my wife, worked on that Pontedero here, you can see. But this was an accident that you probably, some of you may remember, in '87 there was an accident with a cesium therapy source that was stolen. It caused a lot of pollution and so on. And then with Konijn, where Betje May worked, they required regular safety assessments. So actually we did that with Hydrous 1D here. You can see here how the repository worked, or put the waste in there. And then there was a little bit of a soil, and then maintaining a grass cover. And we did some simulations with hydrous. We assumed that just one-dimensional. We had here a seepage phase. And then very, very interesting would be that we had this concrete layer here that would slowly, over the time of its existence, degrade, and the conductivity would, the saturated conductivity would increase slowly. So, and actually here you see some simulations where the conductivity would be very low. So in the waste itself, the water content would be very small, and then it would go up slowly as the degradation in the lower liner or the upper liner would decrease, and this is then the soil below it. We did some simulations of the cesium, and actually it turns out that it would move very, very slowly. Here, this one is just below the lower concrete, just the lower part of the liner towards the groundwater. The groundwater would be saturated, but it would be going up, and later it would decrease very, very quickly, way below the allowed measurements. Another thing that we worked on, I only showed it very much, was actually a mining milling complex that had some pollution here. This is actually one of these holding ponds, a very nasty material. So we measured a lot of observation wells. Critical was this one well very close to the center. There was actually a ruptured geomembrane. So the water would go down and then eventually go to the groundwater and move down. And they noticed that the level in the holding pond was going down, and they thought it was just evapotranspiration or evaporation, but it was really a leaking of the thing. So they pumped it up later. But here are some simulations. This was the sulfate in the system. You can see it goes down here. And eventually, you know, they pumped it out, put a new membrane in there. So there's no additional thing. But you can see here that the sulfate would move then to the groundwater and then way down. I think I have here, oh yeah, that works. That works. A video, let me just get it. And this was actually the metal plume in the system. So it was very slow, but very interesting is here that they repaired the geomembrane. So they pumped it out to put a new geomembrane in there and so on. But this nasty material stayed in the unsaturated zone. And so it keeps bleeding into the saturated zone, and it would have been better to also remediate that, to just dig it up and pollute some, of course, some other site, but anyway, so it kept bleeding, which was not really a good thing. And this is a little bit the same as what we actually looked at with high-level nuclear waste at Yucca Mountain, close to you know, that below a tunnel or so, there would be a shadow, there would be very little water flow, assuming that the tunnel is made quite nicely. Actually, you can use that with solutions of Philip. Philip was very active in analytic solutions, but you can show that if this is more or less a parabolic equation, that the water content or the pressure head along the curve would be the same, but most of the water would, of course, go alongside. And so there would be an area there with very low fluid flow. And then also we looked at the pore scale. Especially we did that with May and the people in Utrecht. Actually, I want to show you one example that where we used the HYDRIS models. This is ink droplet infiltration. It is with what is it, the FIDM, you know, tomography. They determined the hydraulic properties, and you're talking about very, very thin. This is infiltration into a sheet of paper. And it had a coating and then a fiber layer in the middle. You're talking about, you know, microns. See if that goes. And here is a simulation. So this was done with pore scale modeling, where we had the hydraulic properties, capillary pressure saturation, and also the hydraulic conductivity. And then we could simulate that with hydrous. You can see here, now this would be ink in the water that goes into the coating layer. And then the idea is to have a very sharp front. See if that goes again. But then you have a very sharp front, and that very little would go in the fiber layer. Okay, that's basically it. So, just a few slides. I have three more slides I want to finish up, if that's okay. How do I do? Okay, let me. So here, there's a look ahead. Now I say, you know, there's a lot of challenges in terms of taking care of this planet. You know, the surface is increasingly being altered, severe degradation, urban pollution, and so on. But also, there's a lot of progress. Actually, when you look at the amount of material that's being published now, the number of scientists that focus on these issues is really tremendous. And there are still some issues here and there, but everything, and this is the bottom line here, what I'm saying, that everything is accelerating. If you look 100 years ago, what happens was very, very, you know, steady, but slow. Now everything is fast. And it's really a lot of pressure also in terms of young scientists. You have to produce, including the stuff I did, you know, when I studied, basically water retention, a few things. Now people are supposed to, you know, you're supposed to look at really everything. So much is going on, including now here, I put at the end, you know, artificial intelligence, machine learning, and so on. There's a lot of pressure, and everything is accelerating. People ask me sometimes if I go back, what I focus on. I probably would focus on root water uptake still a lot, and maybe on pore scale modeling, where all the processes are. And then here, this is basically the end. The focus of this talk is really on soils, as you know, the most important porous media that we have is the soil below our feet. And we benefited a lot from many of the other disciplines, as you can see here. But at the same time, there's also an outgoing benefit, that what we did was really helping quite a few of the other disciplines. So there is really no clear distinction between agriculture in that sense and the more broader world of porous media. And this is basically the last thing, you know, again, everything is accelerating. There's a lot of pressure to be more productive, to be more efficient, to be more creative, to think big, to have impact. Join the rat race. Run. And sometimes I think it's not good. It's, you know, when people do their stuff, take your time in working out things. Don't worry too much. Unfortunately, you know, instead of, you know, one publication when you're a scientist in a university, what was the norm? Now you have to have 3 or 4. You have to write proposals. You have to serve on committees. You have to be an associate editor or something. So there's a lot of pressure. You can see here my grandson, 3 years old, and he barely can put his head up, but he's already searching. I mentioned that at the Brazil Interpor meeting. You know, he's already searching where to put the next synchrotron or so. So, well, maybe we should also slow down sometimes and really look at things from a very calm way, and don't worry too much where things are going. And that's what I did. I never knew what would go on a year or 2 from now. In that sense, start enjoying things in life a little bit. Thanks. There's so much to talk about, and yeah. Oh, it doesn't matter. Oh, okay.
Bom dia a todos, todas. Tenho aqui uma dupla satisfação, né, de estar aqui nesse momento. Primeiro, por reencontrar alguns amigos, né, colegas como o professor Zago, Bafa, Jolie, que fizemos algum trabalho juntos, sem nos conhecermos, o Fernando, e todos vocês, tá? E todos aqueles também que irão posteriormente olhar essa conferência. Segundo, porque eu volto a encontrar com o professor Van Genuchten, e ele tem essa equação, quem está na área de ciência do solo, de física de solos, e mesmo em outras áreas, como ele mostrou agora no final, conhecem, portanto, a equação de Van Genuchten, né? Então, é a equação mais popular, vamos dizer, da literatura científica, quando a gente pensa em atacar esses problemas que ele mostrou aí. E a primeira, então, eu já conhecia pela literatura o professor Van Genuchten, mas isso era 1988, eu me encontrava na Universidade da Califórnia, em Davis, trabalhando com o professor Don Nielsen. Don Nielsen foi uma grande liderança, uma das principais lideranças nessa área de água no solo e também contaminantes, visible displacement, né? E eu havia trabalhado com tomografia, aqui com o professor Sérgio Mascarenhas, aplicada a solos. E nós tivemos a honra de introduzir a tomografia computadorizada na física, na ciência do solo. E eu fui para lá como cientista visitante, e o professor Nielsen estava empolgado com a tomografia, mas ele tem uma crítica muito forte, que era a seguinte, isso que eu vou falar, porque o professor Van Genuchten estava lá. Então, o professor Van Genuchten foi visitar o professor Nielsen no Wehrmeyer Hall, né, em Davis, e eu tinha recém-chegado, e o professor Nielsen falou para o professor Van Genuchten da tomografia, e que ele tinha visto isso nos meus trabalhos, e nós tínhamos começado uma linha de construir o que nós chamávamos de mini-tomógrafos aqui em São Carlos, aplicado à agricultura. Isso prosperou bastante, tivemos até um projeto temático aqui da FAPESP, né, lá atrás, eu tive a honra de coordenar, e eu estava então muito empolgado, para mim tudo poderia ser resolvido com tomografia, né? E o professor Nielsen pegou uma ponta, um pedaço de lápis, fez um desenho na minha frente, na frente do professor Van Genuchten, porque eles estavam discutindo exatamente isso, quer dizer, essa interação da água com esse meio poroso, solo, partículas, né? Textura, estrutura, tudo isso que muitos de vocês já sabem. Agregados, né? E como lidar com isso. Do ponto de vista experimental e do ponto de vista teórico também. Como o professor Van Genuchten é muito completo. Vocês viram que ele trabalhou e trabalha com as duas coisas. Só que o professor Nilson fez um pequeno desenho que era assim, olha, uma fonte, um detetor e uma amostra no centro. Isso era tomografia, igual a tomografia médica, né? E aí ele falava, ótimo, tal, só que a resolução desse negócio é milímetro, né? Falava em 200 milímetros, 300 milímetros. Né? E ele falou, olha, nessa dimensão, nessa escala, não vai dar para fazer muita coisa, felizmente. Então, isso foi dito na frente do professor Wagner. Né? E eu lá, como um jovem que havia chegado frente a duas autoridades. O professor Nilson foi presidente da Sociedade Americana de Ciência de Solo, presidente da American Agronomy Society, presidente da American Geophysical Union, né? Então, eu estava ali na frente das maiores autoridades nessa área. E eu fui, de certa forma, desbancado lá com a minha ideia de fazer tomografia. Mas eu reagi e falei, olha, mas é possível baixar a resolução, ou seja, melhorar a resolução, seria baixar, né, de milímetros, pelo menos. E com isso eu fui parar em Lawrence, Livermore. E porque lá havia um tomógrafo e um acelerador que fazia com que houvesse fótons suficientes e fluxo suficiente para atravessar uma amostra e fazer tomografia. Depois eu fui até lá, preparei as amostras junto com um colaborador da universidade, mas chegando lá, eu não consegui entrar, porque quando eles olharam meu passaporte, o passaporte era do Brasil, e aí eles falaram, olha, classified, quer dizer, você é sensível, o Brasil potencialmente pode fazer uma bomba atômica. Eu estou vendo aqui você. E você vai ficar aqui. Na salinha lá, tinha bolacha, lanche, coisa bacana, né? Não pude entrar. Nós fizemos experimento com mais que uma fase, né? Trabalhamos com 2, 3 fases. Interessante, publicamos, tudo mais. Depois eu vim saber que ali eles planeavam, né, a bomba atômica. A bomba atômica não pode ter fraturas, bolhas, nada disso. E esse tomógrafo era especial para fazer isso. Então aí, depois ficou claro para mim, fácil de entender, por que eles não queriam que eu entrasse lá. Né? Eu conto essa história para dizer o seguinte, passaram 35 anos. E o professor faz aqui um excelente review, né, daquilo que ele fez e daquilo que foi feito nessa área de física de solos. Eu acho que não poderia ser melhor do que ele fez. Né? Também os exemplos que ele deu, também as outras aplicações. No momento em que nós estamos falando em mudança climática, nós estamos falando em extremos, né? Nós estamos falando em alta temperatura, baixa umidade, alta umidade. Tanto que ele falou que no final ele estudaria evapotranspiração, evaporação. Né? Nós estamos falando em carbon sequestration, aquele sequestro de carbono no solo. Nós estamos falando em mercado de carbono, em gás do efeito estufa. Né? E ele deixou claro que essa camadinha de solo, também chamada de risosfera por muitos, ela tem um papel fundamental para a existência da vida humana. E hoje esse é o drama que todos nós estamos vivendo. Né? Será que nós teremos mais 10, 15, 20 anos, no ritmo que a gente vem vindo, de alteração das condições ambientais, tudo mais? Então, estudar isso é fundamental e explorar. Mas eu queria aqui fazer uma única pergunta. Passaria horas aqui, mas é bom saber que ele está indo a Rio Claro, não é isso? Are going to Rio Claro, professor? Yeah. Então, muito próximo. E agora, uma próxima ida, eu espero que a gente leve a São Carlos. Né? Eu acho que aqui tem algumas coisas, como a cooperação internacional, que é fundamental. Ter uma pessoa como ele, que está no Brasil, um privilégio. Né? A vivência internacional dele, a contribuição científica, a aplicação disso. Todos são lições, eu acho que a gente pode aprender muito mais. Estou vendo aqui vários jovens, né? E aproveitar isso, né? Na universidade, na Embrapa, em tantos lugares aí, que nós fazemos ciência aplicada, considerando que a agricultura é a principal fonte, né? O principal motor, vamos dizer, da economia brasileira, né? E também as consequências que a agricultura gera no ambiente, tanto positivos como negativos. Também ele mostrou aí, falou muito do transporte de solutos na região não saturada do solo. Um grande problema. Como é que os agroquímicos caminham, né? Tem risco, não tem? Um determinado pesticida, e aí vai. Então, há grandes desafios e ele foi ótimo nisso aí. Teria duas perguntas aqui a fazer e quero deixar, obviamente, alguns tempo, né, para que vocês, principalmente vocês, façam perguntas também. Mas só para começar a esquentar, é o seguinte, professor, excuse me if I talk in Portuguese now, but you have the translation. Primeiro, essa evolução que houve pelo lado experimental. Hoje a gente faz tomografias de maneira não destrutiva de amostras de solo em escalas micrométricas, em 2 e 3 dimensões, e duas características importantes, a distribuição de poros nesse meio poroso e a interconectividade entre eles. É fundamental para a gente falar depois em água, falar em fluxo e, portanto, começar a dar talvez um outro enfoque. Por que essas duas coisas não têm trabalhado juntos ainda tão fortemente? O professor mostrou no final uma publicação com tomografia, né, quando é possível fazer 2 e 3 dimensões. Então, essa é uma pergunta. A pedologia não deveria estar mais junto da hidrologia? Uma hydropedology, não? Porque essas coisas ainda andam muito separadas, na minha visão. E hoje seria fundamental a pedologia trabalhando mais com o solo, com a matriz, né? Enquanto que a hidrologia trabalhando mais com a água no solo, com todos esses processos que você mostrou. E a segunda é uma questão que eu tenho há muito tempo, é o seguinte, quando a gente está em física, o Rafa está aqui, não sei se tem mais colegas aqui da área de física, né? Não. Mas física é o seguinte, muitas das soluções são via conservação de energia, balanço de energia, e não balanço de massa. Toda essa conta do Richards e depois o fitting experimental com a formulação, com o modelo de Van Genuchten, ele é baseado num balanço de massa. E o balanço de massa, na verdade, gera uma equação que é uma equação vetorial, 3 dimensões, 2 ou uma reduzida. E essa equação vetorial sempre é muito mais difícil de resolver do que uma equação escalar, que seria a conservação de energia, baseada em energia, inclusive entrando termodinâmica. Então, tem duas perguntas que eu espero que você possa ter entendido quais são. E depois quero abrir aqui a todos, a audiência, né, para ficarem muito à vontade. Nós não podemos perder essa oportunidade de ter o professor Van Genuchten aqui, corpo e alma, né? Nossa presença, podendo conversar, e ele falou, pode ser informal, vamos fazer a coisa mais informal possível. Então, fiquem muito à vontade e já vão pensando aí em alguma coisa que está lá no fundo de vocês, ou não está bem na superfície, vocês estão enfrentando nas pesquisas, nos trabalhos de vocês, né? Vamos aproveitar ao máximo o professor Van Genuchten. Please. You talk now.
what specific question? This is
The first question is how the approach in soil physics mainly is based in vectorial equation, 1D, 2D, and 3D. And it's more complicated to solve vectorial equation like mass balance compared to energy balance. Why we don't have energy balance equation, and why we don't work very strongly with this approach? This is the first. What do you think about?
Yeah, no, I think it will be done, but yeah, we're really lacking comprehensive theories, and I'm sure it will. You know, if you look at the Richards equation, 100 years, you know, numerical solutions, this and that, enormous progress, but there's a lot of stuff to be done, and I completely agree that and you can make it a little bit more general even, that we lack comprehensive theories. You know, even the Richards equation, in many ways, it's a lumping of processes, and you can then do approximations. You know how the hydraulic properties change as a function of salinity, of temperature, of whatever it is, but it is all quasi-empirical, and I'm sure that eventually some smart guys, you know, maybe you or maybe your descendants, but will come up with something that will happen. I remember, you know, you were talking about aggregated soils, or you know,
Preferential flow.
structured soils, but actually Don Nielsen was really at the forefront, because he showed that already about 120 years ago, we knew that the hydraulic conductivity, if you extrapolate from soil texture, the saturated conductivity, or the field values, it's about 1.5 orders of magnitude difference. And nobody could explain this a little bit, but now we know, you know, it's the natural macroporosity of the soil that has nothing to do, or very little to do, with soil texture. But I'm sure that eventually everything will be on the chopping block, and that, you know, but you know, you look at the Richards equation compared to the amount of time we have been manipulating soils for crop production. We're talking about tens of thousands of years, of 3,000 years irrigation. The Richards equation, Darcy equation for water flow, what is it, 150 years ago? It's nothing. Unfortunately, right now, everything is so fast, we even have doubt if this planet still will exist, the human race, you know, because we develop so many more dangerous stuff. We play with our climate, this and that. We can think ahead 5-10 years, but not 100 years. People are not concerned about necessarily their grandkids at the time when their grandkids show up.
Thank you.
Is this? Yeah, you know,
Yes.
I don't have a ready-made solution how to include energy more, but I'm sure, you know, people will come up with something, and it may be radically different.
Good.
In that sense, you know, they say often, you know, don't reinvent the wheel. Don't reinvent what has been going on. Well, it's probably true, but sometimes it's good to be a little critical of what we have. But you have to take your time. This is not something you can do in a night.
The second is how you see the future steps ahead concerned to soil physics. I think soil physics is going to be funded Biophysics will be valued by the society, by the market. How will see that?
There are two parts of it.
Just a moment. Just to give an example, in Brazil, soil physics, we have in agronomy, soil science, and soil physics is, we have Klaus Reicher, Paulo Libardi, a few people work in soil physics in Brazil. So how is the future? Is going to be to enlarge that, or will disappear? Is that a problem of Brazil only? Problem in Brazil, or
Yeah,
other parts?
I think that soil physics will only grow as part of a larger group. We learn, that's actually at the end of my presentation, we have learned a lot from other disciplines, but other disciplines also benefit from us. But there is a lot to be done, and I think going at the pore scale, everything is, the processes occur at the pore scale. And so whether it's pore network or even more refined approaches, that's where the processes occur. And give it 10, 20, 30 years, but people will become more and more, and our techniques, the way we can observe things at the micron scale or at the is increasing enormously, and so I think people will make progress in that. At the same time, interdisciplinary. And I would not say, soils. I'm not really call myself a soil physicist anymore. I'm a Vedozone hydrologist or a soil hydrologist or whatever I am, and I'm not really too much concerned about it. But I know that there is work to do, and people need to slow down. Because there's, we do so much superficial stuff. We need to look at, and a little bit like you said, we need to look, take the time to look at small things that may or may not be at the bottom of big changes. And it will be. But when I grew up, there were what, 1,000, 2,000 scientists in soils. And in hydrology. Now we're talking about, 100,000 in the world, There's so much going on. We used to have 1 or 2 journals that I would look at. Look, you go to the library or online. How many? Either you do research or you read about research, but you cannot do both. So much is going on. It's depressing nearly.
I will stop asking because I still have another question. There's the big data and upscaling and downscaling. How could we deal with this problem? Because the big data, we have all the scales there in data.
Yeah.
And now we need to work with the big data. So, but I will leave to the audience. And I falo em português. Professor Joali, por favor.
Well, professors, thank you very much for your talk. So give you a review of the history, how all this evolved. I've been working for many years with restoration of riparian vegetation that is seasonally flooded. So it's flooded. You have the saturation of this top soil that you call it the unsaturated level. But when you saturate it with water, the chemistry changes and everything changes. Unfortunately, we don't have equations for that. But one of the things that happens also is that the water that comes in brings silt and clay, and this will slowly deposit into the soil and change porosity. So these changes, how will they affect when it becomes dry again? Will they change the flows of water with time? Because this is a process that happens every year.
Yeah, no. Many things will happen, and it depends on the type of porous material that goes down. If this clay, you will have, or silt, or small, inert material. It depends on the clay mineralogy. It depends on whether or not there is biological activity, plant roots, and this and that. So there are many changes, and yeah, it's not easy. But these changes occur over not just months or years, but over tens of years or longer. And the mineralogy, of course, plays a big role.
Plants that are growing.
Yeah.
Because
Yeah.
the soil is changing.
Yeah. But then there is also feedback from the plants. So the plants can change the hydraulic properties.
Por favor, só peço para se identificar.
Okay, sim. Hello, Professor van Genuchten. I'm Dean Hesterberg. I'm actually from the United States, but I'm working here in Brazil at the Brazilian National Synchrotron Light Source, the Sirius Synchrotron.
Here in Sao Paulo.
Exactly, in Campinas. And hopefully we'll get
Or
you
in
over to
Campinas.
visit at some point.
Yeah.
I really enjoyed your presentation, very nice. And what's so nice about your career is that you did work at different scales and you're expanding down to the micro scale, but yet your models are amazing because they're really bridging these scales, right? You're working at pore scale and soil structure and then being able to make field predictions.
Yeah.
My question is this. As we get down to that micro, finer and finer scales, we understand more processes and more details. And what do you see are the limits for upscaling that? I mean, you can keep incorporating into the models, but imagine your elements becoming micro type size and very complicated processes and reactions. Where are the limits to this?
I completely agree with you. That's the upscaling from not just the pore scale, but from the micron scale, and from actually my son is working on arsenic pollution and remediation, and it's really the molecular scale where things are happening. And then you can do some experiments. You can work with pore scale, and then try to analyze that with a continuum scale model. A lot is being done, but I'm sure there will be more progress on that. And yeah, no, the synchrotron, is very, very impressive way of doing things. And yeah, how to go to the continuum scale. And the continuum scale we need if we go to the larger scale, the field scale.
So it is important to keep looking at
critical.
these processes.
It's critical.
Yeah. Okay.
And I'm very much a proponent of the synchrotron type research, because that's where it's going, And then the question indeed is, how can we take advantage of that knowledge and import it up to the larger scale?
Great. Thank you very much.
Yeah.
I enjoyed your talk.
Com placer.
Por favor.
Esther Hamburger, University of São Paulo, School of Arts and Communications, and part of the committee that organizes the conferences. I enjoyed very much your talk, and especially your interdisciplinary approach. And I would like to know, you had this example in India, where they used the moringas
Paquistão.
Pitches.
Yeah, pitches. So I wondered if in your scheme, is there a place for the social sciences and for culture and for arts, in the sense that these dimensions are all involved in like local knowledges, and also if we want to change ways of farming, what's the role for the social,
Yeah.
the humanities, the social sciences, and the
Yeah.
arts, if
Yeah.
there's any?
Yeah. There are enormous a number of ways of improving things, you know, at the local scale, at the small scale, you know, and things. Unfortunately, a lot of the things are still run in terms of economics, in terms of how society is organized, you know, and whether or not sometimes even in Brazil here, how to implement more efficient ways of cleaning water, you know, or saving water, you know. And you know, you look at the dry region in the northeast here, you know, and so much is potentially possible, but it's still, you have the socio-economic and political, how to say that, resistances or challenges, how to implement that. And it really involves, you know, not just the methodologies. We know a lot. We actually know a lot how to purify, how to desalinize, how to, you know, with solar energy, how to clean water, how to save water, but how to implement that at a larger scale. It's not just the knowledge, but also, as you said, you know, the social, the interaction with the small scale farmer. That doesn't know, may not be interested, even though it will help, but he doesn't know, or he's getting pressured by people higher up, whatever that means. Does this answer a little bit?
Nós temos mais uma pergunta e vamos encerrar. E vou pedir ao professor Bafa aqui fazer o encerramento.
Because so much is being done, you know. Obviously, you look at that, you know, there are a couple of places that provide this information. So much is done also, like in Africa, you know. Africa, very dry regions and lots of polluted water, and how to get water that people can drink. And it's technically feasible. Economically, it's not feasible at a larger scale. Sorry.
Oh. Hi, Professor. My name is Murilo from State University of Campinas. Thank you for sharing your life experience, all your knowledge. So my question is about machine learning, more specifically deep learning models that we have been using more frequently nowadays. So our conventional models, flow models, transport models, they are based on the conservation law, the mass balance law. And maybe we have a problem of the closure of these equations when we apply them to macro scale. We have many problems to apply these equations in macro scale. And maybe this is a problem of closure of this mass balance equation. So this problem can be because of the data. Maybe we do not, we are not measuring well our data in macro scale, so the mass balance equation, for example, are not closing. Or maybe the problem is the use of these mass balance equations in the macro scale. Just a thought. And in this sense, deep learning models are dealing well with error of this kind of error in data. They are dealing well. So how do you see this? We are training models, and maybe we are not learning more. about our physical world. And in our other view, we can see that these deep learning models are dealing very great with error in data, for example, because error in data can explain the closure effect problem in the mass balance equation. So what is your opinion about this? Are we walking in a good way to training these models, or maybe we should stop a little bit and thinking about our mainstream data? Thank you.
Yeah, you know, I don't have a ready-made solution. I do know that much is happening. And actually, when you look at the experimental procedures now, also at a larger scale, you know, think about remote sensing, whether it's, you know, from satellites or smaller stuff. But so much is going on that gives information that we can use. So it's the upscaling, as Vijay was talking about, but also the downscaling and how to impart that the best way at the larger scale. I never really worked very much at the larger scale, and I very much admire people who do that, because that's where very often the problems are. Not the processes, they occur at the micro scale, but in terms of management, in terms of whatever it is at the larger scale, that's where farmers operate, or that's where you know the politicians operate, whatever, you know. Yeah, so you know, I don't have, you know, you can formulate a Richards equation or whatever it is, and it's there is closure in there, but how to apply that at a larger scale? We worked a little bit with ModFlow, and then couple it with Hydrus and so on, but it's still limited in many ways. But our computers increase, machine learning, whatever, you know, that last thing, or artificial intelligence, new approaches will become available, and they will be worked out, good or bad. Chat, GPT, whatever.
Pedir para projetar um slide, por favor. Bom, antes de encerrar, eu queria mais uma vez convidá-los para as próximas conferências que nós vamos ter dessa série. Então, a gente vai ter uma agora no dia 10 de outubro, está ali o tema, 27, e depois 24 de novembro. Como vocês veem, tem sido um ambiente bastante privilegiado. A gente deveria ter acabado 11h30, meio-dia, ainda estamos aqui. Eu sei que tem várias perguntas que gostariam de ser feitas. Eu também tenho algumas que eu vou guardar para depois, para não comprometer aí os outros compromissos. E, mais uma vez, eu queria, então, agradecer a presença do professor Rien, do Silvio Crestana, que veio aqui atuar como moderador. E, enfim, desejar a todos um bom dia, um bom fim de semana, e espero contar com a presença de todos nas próximas conferências. Muito obrigado.